Okay, today we're going to look at differentiation. Now, based on this question here, we are given a trigonometric expression. The domain given would allow us to perform differentiations because within this domain here, the function itself will be continuous. Right now, that's the fundamentals of differentiation. Now, our task today is to show that the derivative with respect to data here can be shown as this form, right? Where a is a rational constant to be found. All right. Now there are many approach that we can actually apply here to obtain the intended expression. Right. Now one of them would be the most direct method would be to apply the quotient rule. Right. Now I'm going to show you how to actually apply the quotient rule and then obtain the intended expression. Now just to recap, quotient rule, when are we supposed to use quotient rule? Whenever you encounter such expression in this form, a function's y with respect to x in this form, or sometime for simplification you can write as u over v here. Right? So here we can see that this form given here is very much similar to this quotient rule form, u over v. Okay, so therefore that gives us the idea that we can actually apply quotient rule here. Now once we identify that we can apply quotient rule, now what would be the formula for the first derivative for quotient rule then? So the first derivative for quotient rule is dy dx. Okay, I'm writing down the formula for dy dx in this case, which is given by v du dx divided by v squared here, right? Okay, but anyway, this is the formal formula that you can get from the data booklet, right? Now, make sure you know that at this point for this question here, we are dealing with functions with respect to theta itself. So sometimes you might want to be very careful with this. So we're going to write this one down as y equal to u theta v theta here, because it's functions of theta, and then therefore the dy dx, instead of writing dy dx in this case, because we differentiate with respect to x just now, now we are dealing with the theta, so therefore our dy dx would be as such, but the format will still be more or less the same, but we change it to theta instead. V squared. Right. Now I hope that is clear. Right. Once you are comfortable with this, all right, now we're going to get started with the applications of this quotient rule. So first step, we're going to label u as 3 sine theta here, whereas v will be 2 sine theta plus 2 cos theta, and then du d theta, we're going to differentiate that with respect to theta here. If you forgot what would be the differentiations for sine, you can always refer to the data booklet. Right. And then dv dx. Alright, there you have it. And then sometimes you may not be able to remember the formula correctly. So there is a small trick that can help you to regain your memory on that, right? So usually we do it in such a way. If we arrange it in such a format, we can always use the arrow approach just to remind yourself which one you are supposed to put up your numerator here. So here I'm putting an arrow. We go from the ground to up. All right. So that's how we actually pick up our knowledge. So we have to learn it from the ground, going up. Okay. So therefore, that gives us the first expressions on the quotient rule, which is v du d theta. And then thereafter, once you have reached here, we can go down here. Right. So that is the second part. So the first part subtract with the second part here. Right. So that's one way to help you to remember the quotient rule, because it's very similar to product rule. Product rule, we don't really need to subtract. We just need to cross multiply, and then it's an addition, right? Okay, so once we have all this set up, all we need to do now is just to plug and play. Plug in all this result here. So I'm going to label this result here, result number 2, and then substitute it into the quotient rule formula in number 1 here, right? So to do that, I'm going to write it down at the side here so that you can refer directly. Therefore, we can write down our dy d theta here as v. Okay, so based on this, it will be 2 sine theta. All right, and then multiplied by 3 cos theta. Right, we can see it here, and then after that we need to subtract. Okay, subtract 3 sine theta, and then divided by v square. So v square is here. Alright, and then there you have it. We have successfully substituted all the required sections into the quotient rule now. Right? Our next stage is quite direct. All we need to do is just expand the trigonometric expression. So in this case, you can see that we have 6 sine and cosine. This part also we have 6 sine and cosine. So therefore, you can sort of cancel out each other. Okay, so I'm going to write it down in a row so that you can see them directly in action. Okay, so I'm going to write it down here directly from here. You can see that there is actually 6 sine theta cos theta. After that you have 6 cos square, and then after that you have 6 sine cos, and then finally we have that 6 sine square theta. And then there you have it. We have now for the denominator itself, now usually I prefer to factorize it out. So if I factorize that, I'm going to take out 2 here, which will give me a 4. Okay, and then you can see that's how it is at this point. Now you will notice that these 2 terms would sort of neutralize each other, so cancel out. They are the same term. And then what is left is just 6 cos square plus 6 sine square here. And then 6 cos square plus 6 sine square, using that identity. So I'm going to write down some of the identity. You can refer to the data booklet again. One of the identity that I always use, or which is always required in the exam, is sine square plus cos square equal to 1, or the second one. Alright, so from here, I notice that I can actually apply identity number 1. So from here, I will get 6 6 sine square plus cos square over 4 sine theta plus cos theta square. Alright, so there you have it. And then from here itself, you notice that there is actually a 1. Therefore, we can simplify this into this. We can even simplify the number here. So let me simplify everything at once in this case. So once I simplify, and that's 6 divided by 4, which is 1.5. Okay, so we are almost there. You can compare this with this. We are almost there, right? So I'm going to pause here for a while for you to sort of go through the process step by step before I finalize the proof here, right? All right, I have rewrite the dy data that we have obtained previously. This is where we are at this point of time after we apply the quotient rule. Now I'm going to summarize this and then conclude the proof in this case. Right? What we need to do next is pretty straightforward. All we need to do is just expand the new denominator here. Right? So if you expand that, we will have like sine square okay, as you can see there you have it. From here itself, we notice that we can apply that identity one more time. Okay, I hope that you still remember the identity. Right, if you can't, I'm going to write down that identity one more time over here. It's always good as a reminder. Alright, there you have it. So from here, we can group this together, the sine square and cos square. Okay, so from here itself, you found that this is pretty much a 1 from this identity. Okay, as you can see, we are almost there. Okay, and then one last identity that we need to apply will be here. We know that from the double angle identity, sine 2 theta is given as 2 sine theta cos theta. Right? So from here, we can finalize our answer as sine 2 theta. And then there you have it. We have successfully proven this particular derivative. Right? So we can write down as a completion of proof, we just write down proven there. Where the a is a rational constant to be found, we will write down where a is 1.5 then, based on the structure of the derivative, right? So I hope this is clear. This is the one of the methods how we can actually differentiate this particular expression. Okay. Now next I'm going to show you how to actually differentiate this or produce the first derivative using a different approach. Alright, approach number 2. Okay, how can we do it not using quotient rule? Instead, we're going to use a more direct chain rule in this case. In order to apply chain rule, we might have to change the structure of the original expression here. So I'm going to show you what I mean by that. Originally, we were given this. Okay, so firstly, I would always factorize. If you can see any factor, that will be rule number 1. So here you can see that the 3 and 2 can be factorized out. Therefore I can actually write down in such a way. Alright, you can see that this is typically 1.5. Okay, and there you have it. And then in order to apply quotient rule, my advice is we are going to restructure this expression by dividing the numerator by sign, and then the denominator also divide by sign. Therefore, we have, now I'm going to write down what is going on here. So sign divide by sign here, and then the same go for this. Alright, and then from here itself, we can simplify that to 1. This one will be 1 if you divide them, and then this one will be a cotangent. And then there you have it. Right? It looks much more easier. Not really that easy, but it's suitable for applying the chain rule in this case. So we can actually write down in this form. Right. So I hope that is clear. Next, let me show you. Just remember this. This is the form that we have at this point. Let me show you how to actually apply the chain rule from here onward. Right? Okay, thank you. All right, this is where we are at this point. We have obtained the index form for the original expression here. Okay, at this point we are ready to apply the chain rule. Okay, now just to recap how chain rule can be applied. In this case, we are going to let u equal to this expression here. Right. So from here, we are going to differentiate that with respect to theta. Okay, now if we differentiate this with respect to theta, we can actually refer to the data booklet, or you can reapply your chain rule here. Okay, this is simply 1 plus cosine theta over sine theta. Right. Okay, so you can actually apply your chain rule here. Okay, at this point I'm going to apply the chain rule directly. Okay, so we have sine theta and then subtract off with the cos theta. Alright, and then finally we will have this. Okay. So from here, if you try to simplify that, you would basically get like sine square plus cos square here. Alright, you can see that. And then from here, again, we can refer back to the identity again. So here I'm going to write down the identity one more time, just as a reminder. Okay, so from here itself, we know that we have negative 1 over sine square, which is typically negative cosecant, if you like to put it in this form. Right? Okay, there you have it, our dU theta. And then don't forget, since we substitute this term here as u, therefore our y would be 1.5 u negative 1 in this case. Therefore, we need to proceed on by differentiating this with respect to u. Okay. and then from here you get 1.5 u negative 2, and then u is given as such, therefore we're going to put everything back. U squared, so u squared means 1 plus cot10 squared. Right. And then finally, what we need is our dy dx. So dy dx is basically given by the chain rule, which is dy d theta oops, let me see. I think I wrote it down wrongly. Let me change that. I think I get used to the dy dx most of the time. What we need here is dy d theta. So dy d theta is given by dy du by du d theta. Okay, dy du is this. Du d theta is given as such, this one or this one here. Therefore, we have negative 1.5 by du d theta. Du d theta is this. Up to you. Maybe I prefer to write down this one. And then we are almost done. From here, I'll try to polish it a bit. You can see that negative 1 and negative multiply each other, become positive. Therefore, these two, because they have the same power here or index, I can join them together. I can expand it into that expression itself. So therefore, I will have cosine theta squared. Alright, as you can see, this is the same expressions that we have already obtained previously, right? So I'm going to finish this up. Let me erase off these sections that we don't need. I'm going to pause here for a while so that you can check through. This is our current final answer here. Okay. Now let me erase off this. Okay, and then from here itself, I have my dy d theta, which is given by 1.5 Alright, and then as usual, you're going to expand that. So as you would expect, we will end up here. And then again, by using one of the double angle identity, you have sine 2 theta equal to 2 sine theta cos theta. So from here, we can simplify this as 1.5, 1 plus, okay, these sections can be written as sine 2 theta. And then there you have it. We managed to prove this using chain rule instead of quotient rule, where our rational number a is equal to 1.5 here, right? So I hope this will be useful for some of your learning. Until I see you again, okay, take care everyone.